16 out of 22, so. So a lot of things are similar between sort of continuous and discrete random variables. Some things are different. I'll say the first thing is I'll start using, instead of the word random variable, I'll start using the word distribution more. And distribution is just sort of tells us we could use it with discrete also, but it puts more of a focus on the particular function that we're going to be interested in. And so you'll hear me say random variable, sometimes you'll hear me say distribution, sometimes they mean the same thing for our purposes. So instead of probability mass functions, which we had in the continuous case, or in the discrete case, we now have probability density functions, PDFs, instead of PMs, right? My probability mass functions do not tell me particular probabilities, but they're used in calculating probabilities. Okay? So my probability density function has to be a non-negative function, right? It can only take 0 or positive values that come out of the probability density function. And if I integrate from negative infinity to infinity, if I calculate the area under the curve, it must equal what? Okay. Why? Because I compute probabilities with continuous random variables by using the sum version for functions, which would be the Riemann sum, right? Which is a definite integral. So if I want to know the probability that my random variable, my distribution, takes values between some value a and some value b, then I would calculate the definite integral of my function, f of x dx, from a to b. So I have some function here, and I can compute probabilities. I guess I'll have to go to 0 at some point. Probabilities from a to b by computing the area underneath the curve. Okay? Which is why, if we go back up, the area under the curve has to equal 1, because if I want the probability of sort of anything happening, probability, right, the area under that curve should equal 1. Okay. So it's only a legitimate probability density function if it's a non-negative function and the area under it's 1, and then I'm computing probabilities by finding other areas under curves. Okay. We're going to be working more with the cumulative distribution function. Remember, the cumulative distribution function is this function capital F of x, and it is the probability x is less or equal to x. So, I have, let's just say this is my probability density function. My cumulative distribution function is telling me how much of my probability is to the left of a particular point x. And so probability x is less than or equal to some value x. And I would answer that question by taking the definite integral from negative infinity to x of my probability density function. It's typically thought bad form to use the same letter here as you use up here. Right? And so I put a u there, but sometimes I'll just break that form. I don't care if I have that form that much. So anyway, but the idea of I would compute the area under the curve going from negative infinity up to a particular point. And that'll be helpful because if I want to compute the probability, right, if I want to compute a probability from A to B, it turns out, right, I could just plug B into my cumulative distribution function and then plug A into my cumulative distribution function and subtract the two. Right? I just figure out how much area is to the left of B, and then I didn't want the area to the left of A, so I'll subtract that thing off. So that's one reason it'll be helpful. Probability doesn't occur at a point. Probability occurs over intervals. If I integrate, how could I see the probability doesn't occur at a point? If I integrate from A to A, doesn't matter what function I have, it will be 0, right? Because if I have no width, I have no area. Okay? So probability doesn't occur at points anymore. The likelihood that you'll get any particular value out of a continuous random variable is always 0. We have to use intervals to find probabilities. Okay. And then I'll just say, also with expected values, and then we'll look at the uniform random variable in a little more detail. Expected value is equivalent to what we did before. If I want to know the expected value of a continuous random variable, instead of summing x times, the probability mass function, I will integrate upon the definite integral from negative infinity to infinity over all possible values, x times the probability density function, right? And if I want to figure out what the variance is, I need the second moment, the expected value of x squared, and that would be the integral from negative infinity to infinity of x squared times f of x, right? My probability density function times dx, right? So everything is equivalent. It's just we're going to be working with definite integrals instead of sums. It actually oftentimes becomes easier. Students usually are a little more confused with sums and series in Calc 2 than they are with the integration techniques, although they can all cause some issues. You may want to go back and pull out your calculus book and just review a little bit. We will need, what will we need? We'll need integration by parts, U substitution, I think that's it. Yeah, partial fractions I don't think we'll need. Trig subs, no. Yeah, I think that's it. So it wouldn't hurt you to go back, review a little integration by parts, make sure you know your U substitutions. Those are the ones that come up sometimes. Okay. All right, so let's see. The named ones, uniform. Two parameters, A and B. So a uniform random variable is a constant function over that interval from A to B, and it's 0 otherwise. So I guess it's constant over that too, right? It either takes the value between A and B, right, some constant value, and outside of A and B it's 0. If it's 0, then it provides no probability of things happening, and it's like, so uniform just means it's all equally likely. The height of my probability density function is telling me how likely it is to end up in a particular area. And when it's constant, it means if I keep my widths the same, that the likelihood I end up here versus here versus here, as long as I keep my widths the same, versus here in my distribution, they're all equally likely. Okay. If there's a part where the probability density function is twice as high at one part than the other, then it would say the probability of ending up here would be twice as likely as the probability of ending up here. Or in that small neighborhood, again, given that we're talking about equal widths. So the height of the probability density function is telling me a likelihood of ending up in a particular area, and so I can sort of compare different areas. Right here, since this is, compare this here to this here, and I'll say this is probably about 5 times as high as this, therefore it's 5 times as likely I will end up in this region than that one. It's sort of the way that we can think about the probability density function. How much density ends up in that region. Okay. So uniform, everything's identical, so I'm equally likely to end up anywhere. First question is, what's this constant going to be, right? And if the area under the curve, which is really all the area comes in this rectangle, that rectangle has a base of b minus a, so the height should be the reciprocal of that, so the area is equal to 1, so it would be 1 over b minus a. There's my uniform, there's my probability density function for a uniform random variable. And then if I want to compute what's the probability, let's let A equal to 10 and B equal to 50. Then my height of my function is 1 over 40. And then if I wanted to know the probability that x is between, I don't know, what do we say, 15 and 35, that corresponds to 10 and 40, right? 15 would be about right here, 35 would be about, that's 50, would be about right there, right? And I would need to find the area under the curve between in that region. And the nice thing with the uniform random variable is all my areas are rectangles and I don't really need calculus. But I certainly could integrate 15 to 35. my probability density function. Okay. But if I'm dealing with constant functions, then it's a rectangle. The base of that rectangle is 35 minus 15, and the height of that rectangle is my 1 over 40. So I guess it's 1/2. So if I draw from this uniform random variable, then the probability I ended up between 15 and 35 would be 1/2, is what that says. So we'll work mostly with the standard, what I'll call standard uniform, random variable or distribution, and that's when A is equal to 0 and B is equal to 1. And maybe this calculator will work better. A lot of calculators have this random number generator on it, and when you hit random, when you hit random, it gives you some random number that comes out of it. It's trying to approximate what's called the standard uniform random variable, right? Is equally likely picking every value between 0 and 1. So the probability density function for this would be 1, right? B minus A would be 1 when x is between 0 and 1. And it would be 0 otherwise. So I would have this probability density function, 0, 1, height 1, 0's over here, height 1, 0's over here. We'll compute the expected value. Actually, we'll do that one in general, expected value and variance, just to make sure we have a calculation under our belt that doesn't involve any too fancy of stuff. But let's go ahead and figure out for the standard uniform random variable, let's figure out the cumulative distribution function. Right. So remember, that is f of x, capital F of x, that's the probability that my random variable x is less than or equal to some value. That's the definite integral from negative infinity up to x of f of u du. Again, bad form to use the same letter here and here, so we'll be a little bit careful with that. Okay. And it's nice because some random variables actually take values all the way from negative infinity, non-zero values all the way from negative infinity to infinity. We'll talk about normal distributions, and normal distributions, which is called the bell curve, right, are called the bell curve sometimes. They take non-zero values. They have 0 as an asymptote going off to infinity and negative infinity. But I actually have to integrate from negative infinity to infinity potentially if I'm going to answer certain types of questions. But a lot of our random variables don't necessarily do that. Uniform is one of them, right? These values are primarily going to be 0. They're certainly going to be 0 outside of the 0, 1 range. So if I'm trying to write down the cumulative distribution function, right, then it's 0 if x is less than 0, right? If x is less than a, right? Cumulative distribution function is asking how much probability is to the left of certain values, and if I pick a value over here, then the answer is there's no probability over there because the value of the function is equal to 0 over there, right? It's not until I pass 0, right, that I start accumulating probability. And so I guess then the question is, if I'm at some value x is between 0 and 1, how much probability, what's the area under the curve to the left of this? Well, the base would be, the base is the distance between 0 and x, which is x, and the height is 1, right? So it would be x. And it'd be something, we could do this in general for the uniform, right, with A and B. Up to A, there's no probability. Once we get past A to B, right, there's some probability. It'll be x minus A, right, divided by B minus A, until we get up to B. But then what happens here in this case when x is greater than 1, once I move past 1, how much probability is to the left? right? 1. I've accumulated all of the probability up to that point. And that's true. Our cumulative distribution functions are the same now as they were with the discrete case. The idea that, as k goes to negative infinity, then it should give me 0. And as k goes off to infinity, my cumulative distribution function should be approaching 1. And we saw that with the binomials and the geometrics, and we could see it with negative binomials and so on and so forth. So this cumulative distribution function is going to give us the probability up to a certain point. And so here's what it looks like. It looks like 0 up to 0. And then from 0 to, here's my 1, right? It will increase as y equal to x, right? And then once I get past 1, I've accumulated all the probability. There's no new probability to accumulate. And so that's what it would look like. And if I plug a value into this, it's telling me how much probability is to the left of a certain value, right? The area up to a certain point of the probability density function is this one right here. Okay. Which actually tells us something, and I write that in. Right? The derivative of the cumulative distribution function will be the derivative of negative infinity to infinity of f of u du. And this is just the fundamental theorem of calculus back from Calc 2, Calc 1, Calc 2, right? Fundamental theorem of calculus part 1, and that is, if I want to take the derivative function of something that looks like this, oops, that should have been an x, negative infinity to x, right? Of a function, I create a function, the area up to function, the derivative of that is equal to just the original function that I started with this variable plugged in. Okay. Which tells me the relationship between the probability density function and the cumulative distribution function is that of an antiderivative, or if I go back this way, a derivative. So as long as I can calculate derivatives and antiderivatives, I could move back and forth between probability density functions and cumulative distribution functions. Okay. And when we start dealing with multiple random variables at the same time, then it'll be partial derivatives, right? Well, I'll take derivatives with respect to one variable or another one. Okay. And again, it's typically, I know antiderivatives aren't always easy to calculate, but typically antiderivatives are easier to calculate than partial sums. Okay. So that's why we're going to be using these things more often. All right, so let's just see an example of this. I'm just going to have this on for a minute. Oh, could you pull that cord down? So people can see a little bit nicer here. So let's see. Oops, I don't have. Nope, I didn't close it. All right, so we're still going. All right, so right here. So here's let me just take a uniform distribution. Okay. I'm going to take 1,000 things from a uniform distribution, 10,000, I'm sorry, I have 10,000 things that I'm selecting from that uniform distribution. Just give me a couple of the ideas. If I don't put anything other than R unit 10,000, every random variable on R has a standard values for parameters that they would use. And so if you don't put anything else, then it's assuming A is equal to 0 and B is equal to 1. So notice all those numbers are between 0 and 1 there. And if I look at the histogram of that, right, I get all the way from 0 to 1, I get equally likely values coming out of that random variable. Okay? Approximately. Of course, there's always a little bit of noise in there, otherwise it wouldn't be probability. If everything fit perfectly. But if I were to draw and sort of drop everything into the proper bin, I see, it should look an awful lot like my probability density function, maybe with a little bit of noise attached to it. And if I plot the cumulative distribution function, it should look like, oh, that looks pretty good, right? It should look like this, right? It's 0 up to 0. That's from my sample there. It's just calculating what percent of the results were to the left of a certain value, and I can see as I go from 0 to 1, it looks like a linear function, x, which is what I expected it to, and then so once I get past that, then it's constant 1, right? Everything past that, we've moved past all of the new probability, everything's to the left of that. If I make it a smaller sample, of course, 100 things, right? It's sort of the same thing. There's just more chance. I mean, the larger the sample, the more it should look like the probability density function. But the idea is that every time I do that, it might look a little different. But sort of on average, I expect it to be uniform. Right? And then if I plot the cumulative, right, the same thing. It's trying to approximate this cumulative distribution function here. All right. If I'm really interested in, let's put it back up to 10,000. I could go from 10 to 50. Is that the example I looked at? Right? And now it's giving me a random sample of values between 10 and 50. And if I look at the histogram, right, same thing between 10 and 50, uniformly distributed. If I plot the cumulative distribution function, again, it's the equivalent to this, starting at 10, going to 50 with the straight line. I can figure out the antiderivative of that, and so on and so forth. Okay? So, that is the idea of the uniform random variable. I'm trying to decide if there's anything else we need to say about, expected values. Let's compute some expected values. Just to get used to it. Just to remember what taking an antiderivative looks like. Although these aren't too terribly. So let's work with this, and let's compute the expected value of x. Which means I need to integrate from negative infinity to infinity x times my probability density function. But of course, my probability density function takes 0 at almost a lot of the values, right? And so I'm really just integrating from a to b, and I'm integrating this function x times 1 over b minus a dx. Okay. So this is a constant, I can pull it out, 1 over b minus a, and then I'm just integrating x with the antiderivative of x. X squared over 2, and then I'll plug in my b and my a. Right? And then the fundamental theorem of calculus says, okay, this should be b squared minus a squared over 2 times b minus a. Okay. Put this together with that, and then I'll get my b squared minus a squared. And b squared minus a squared I could rewrite as, how does that factor?
B plus a, b minus a.
B plus a, b minus a, so I get my b plus a, b minus a over 2 times b minus a's cancel out, and I get b plus a over 2. I no longer have my function, right, but what does b minus a over 2 tell me? Right? What's the relationship of b plus a divided by 2 with a and b? Well, b plus a over 2 is?
The mean.
The mean of the two, right? It's the midway point between a and b. Is the average value, is the midway point between a and b. And given that everything's equally likely, everything seems very nice and symmetric, if I'm going to pick values between a and b, right, I expect on average to get something that would be in the middle, which is what we call the mean. Okay. So that's not a surprising result. Actually, we probably would have been surprised if we would have gotten something else. So the expected value will be the average value of the two endpoints for a uniform random variable, which says for the standard uniform, the average value should be 1/2. Okay. What else do we need to know about this one? Let's go ahead and compute the variance, which means we need the expected value of x squared. We need the second moment. So we need the integral from negative infinity to infinity of x squared times f of x dx. Right? So we just calculate these things in exactly the same way that we calculated them before, only we have Riemann sums instead of sums. Again, my probability density function only takes non-zero values between a and b. So between a and b, it's x squared times 1 over b minus a dx. Right? And it's 0 everywhere else, so that's just going to give me 0 area. Okay. And again, I could factor out, I could pull out this 1 over b minus a. Take the antiderivative of x squared, I get cubed over 3, a to b. Plug in my endpoints, fundamental theorem of calculus, part 2. I get b cubed minus a cubed over 3, I have that 3 there, b minus a. And then I can factor, this is, just like this was a difference in squares, so b minus a ended up being b plus a times b minus a. This is a difference in cubes, and so, at least if you know the formula, like any other factoring, there's a reasonably nice formula there, and it looks like b minus a times b squared plus ba plus a squared. Okay. So you can factor the difference of cubes. You know, we could figure out the third moment, it'd be the difference of quartics, right? Same thing, but we're going to stop here, and then we have our 3 and our b minus a here, and then that cancels out with that. Okay. Which tells us our second moment is b squared plus ba plus a squared all over 3. Okay. So that is not the variance, right? What do I have to do to find the variance?
Subtract the square of the expected value from the second moment.
Yep. So the variance of x is the expected value of x squared minus the expected value of x squared, right? And typically those two things are not going to be the same value. So we just found this one is b squared plus ba plus a squared over 3 minus, and then this one squared would be b squared plus 2ab plus a squared over 4, if I square that. So I suppose I need a common denominator, so I can do a 4 in the denominator and a 4 in the numerator. I can do a 3 in the denominator and a 3 in the numerator up here. Okay. Looks like I'll get something like, well, the whole thing will be over 12. And then what do I have here? Let's see. I have a 4b squared minus 3b squared would give me a b squared. Okay. I have a 4ba minus 6ab would be a negative 2ab. Go back through and double check and make sure. And then for the a's, I have 4a squareds minus 3a squareds. 4a squared minus 3a squared is plus an a squared. Right? And then everything's over 12 was my common denominator there. Okay. And then what's b squared minus 2ab plus a squared? That factors to b minus a squared over 12. Okay. And how do I see b minus a? Right? So b plus a over 2 was the midway point. What's b minus a? B minus a is the width of it, right? And if the variance is somehow telling me how spread out things are, it makes sense that it should at least somehow depend on the width of the interval, right? B minus a is telling me how wide the interval is. It's saying, oh, you want to know the variance? Take the width of that interval, square it, and divide it by 12. Why 12? Well, that's how it all worked out, didn't it, right? That was our integration and our common denominator, right? That's just how it worked out. But essentially, it's the width of the region, square it, divide by 12, that gives me my variance. That tells me how spread out things are. And again, that makes, at least makes sense in hindsight that it would depend on the width of the, if I'm talking about the spread. Okay. So the standard uniform random variable then would have mean equal to 1/2, expected value equal to 1/2, and it would have, I'm just going to use this notation, it would have variance, which we sometimes call sigma squared, as 1 squared divided by 2 is 1/12. It's somehow telling me how spread out that is. Okay. All right. Okay. That's our, right, so that's how we would calculate, again, expected values, second moments, variances. Anytime we deal with a continuous random variable, right, we're integrating things. We're taking x times our probability density function, we're integrating it. So when we deal with the exponential random variable, which will be the next one, then we're ultimately going to have to integrate something that looks like x times e to the negative lambda x dx, and that's where you're going to need your integration by parts. So, go back, make sure you spend just a little bit of time reviewing it. It's not the most important part of this class, but it's very helpful if we can do the calculations with it. This is the particular integration by parts that will come up in the not too distant future. Okay. All right. One other thing, what do we have here? A little over 15 minutes. One other thing that's attached to that, so we have our expected value and we have our variance. We know how to calculate moments now, at least we've seen examples. We have a couple of other things that are going to start becoming more valuable to talk about, and they're called quantiles. And I don't think the book uses alpha here, but I'll use the term alpha because we oftentimes see it as the alpha quantile. And the alpha quantile would be asking, it would be some value, oftentimes a Q of alpha, Q for quantile, right, would be the probability that x, and this isn't just true for uniform, it's true for any continuous random variable. In fact, it's true for any random variable discrete also. It would be asking, okay, what value could I plug in here, right, so that the probability x is less or equal to Q of alpha is equal to that value alpha. So it would be asking something like, notice this is just the cumulative distribution function. What value can I plug into my cumulative distribution function to get this value for alpha? Okay. And it's saying, okay, what value Q of alpha can I plug into it so that the area under the curve to the left of that Q alpha is equal to this value alpha. Okay. Now there are some more important and less important values that we're interested in. So we actually use the term median, right, is what we oftentimes will call Q of 1/2 or Q of 0.5. Right? The median is the point in my distribution so that half of the probability, half of the area is to the left of that point, of course, which means half of the area, half the probability is to the right of that point. Right? That's what the median is asking for, right? It's asking, where's the point in here so that half the area, half the probability is over here, and half the area, half the probability is over there. In general, that is not the same value as the mean, which is the mean. When we use the word mean, we mean the expected value. Okay. So it's another thing that sort of measures, the median is another thing that measures the middle of a distribution, but in a different way than the expected value does. For a uniform random variable, they're the same. Right? For a uniform random variable, the standard uniform, the mean is 1/2, the expected value is 1/2, the median, half the probability is to the left of 1/2 and half the probability is to the right of 1/2, but it doesn't have to be that way. And when we go on to the next random variables, we'll see that's not always the case. And then we have things that we call, the lower quartile. Quartile, right? So dividing up into 4, but which is what another name that we make or we give for Q of 0.25. Right? So at what point is 25% of the probability to the left in this particular distribution, which would mean 75% of the probability would be to the right, and then the upper quartile is what's called Q of 0.75, right? So you want 75% of the probability to the left of that particular value, which means you want 25 to the right. Sometimes you take those two values and you subtract them, and that's something called the interquartile range, right? So you have these two quartiles, this upper and this lower, and if you subtract those two values, it'll say, well, how wide is it if you sort of, if you get rid of the top 25% and the bottom 25% of your sample, for instance, right? So these quartiles, but with this quantile, right, means I don't have to take, the quartiles, just the 0.25 to 0.75, 0.5, which is the median. I could use whatever probability. And so sometimes we're interested in things like Q of 0.975, right? Which would really just be asking for, right, the probability that x is less than or equal to 0.9. So 97.5% of the probability is to the left of that point, 2.5% is to the right of that point. Sometimes we're interested in values like that, and when we are, we're talking about quantiles. Okay? It's going to depend on the particular distribution we're working with. The uniform distribution is just sort of boring in this regard because it's exactly where we would expect it to be. Right? The standard uniform distribution, we just calculated the cumulative distribution function. This would be at 0.975, this one would be at 0.5, this one would be at 0.25, this one would be at 0.75, because my cumulative distribution function between 0 and 1 was x. Right? So that's an easy thing to calculate. But in general, we'd have to figure out, okay, what value can I plug into the cumulative distribution function and get that particular alpha out of it. So, cumulative distribution functions, much more useful, going to help us compute probabilities, especially it'll be helpful when we can't find antiderivative functions. The normal distribution, the normal random variable, we will not be able to find a cumulative distribution function for that. So we'll have to have tables of values and such, right, because we don't have a nice antiderivative function for that. But we can, we can figure out ways to approximate it. But I can subtract off values from my cumulative distribution function, plug in my cumulative distribution function, I can solve for those. I can start talking about, probabilities being to the left and to the right at a certain point. I could have done all of this with my discrete random variables, but because my function's not continuous and it makes these jumps, it's a little bit more difficult to talk about those things. All right. Okay. Anything else with uniform? No, I don't think so. Okay. So let's talk about the next one. I think we got all of that stuff, which is the exponential. Exponential distribution. When I say distribution, I mean the same thing as random variable, right? So the exponential random variable. Okay. And x will, that's going to, well, let me write down the probability density function first. Okay. It's going to be called an exponential random variable and exponential distribution because it's going to be tied with the exponential function. So here's a function that's going to be e to the negative lambda t, so I need a lambda out front. Lambda e to the negative lambda t is my is the value of my exponential distribution, my probability density function, when x is greater or equal to 0, and it's 0 otherwise, except for x. So, it's going to, and of course, one parameter, lambda. What other distribution had lambda as a parameter? Poisson, same lambda. And I don't think we'll be able to talk about it today, but first thing on Wednesday, we'll talk about how the exponential distribution is going to be related to the Poisson distribution. Same lambda, right? So it's accounting the number of occurrences, and actually, Poisson random variable was the idea was counting the number of successes when you start breaking up your time interval into smaller and smaller. So every moment you start asking the question, have I had a success? Do I have a success? Do I have a success? Right? Or is it a failure? And so the Poisson was counting the number of successes when you take your time interval and start breaking it up into these infinitesimally small time intervals, and at every moment you're thinking about having a Bernoulli trial, and there's a success or a failure at every moment. Well, Exponential is doing the same thing. It's going to take your time interval and break it up into these smaller and smaller time intervals, and every moment you're going to think about as independent Bernoulli trials, and you're counting until the first success. How long do you have to wait until your first success? Okay. So the Poisson is very closely related to the binomial random variable. The exponential is very closely related to the geometric. It's sort of the continuous version of the geometric random variable, where you're waiting for the first success, waiting for the first occurrence of something. Okay. We'll look at an example of that. And so it shouldn't be surprising then that the distribution looks a little bit like a continuous version of the geometric random variable, whose probability mass function looked like this, only with steps in it, right? And so we would have that at 0, that would take the value lambda, I guess, right? It would look something like that. And of course it's 0 over here. So it might be worthwhile to think about the cumulative distribution function, because if I want to compute any probability with this, I'll probably want to use the cumulative distribution function, unless I like to do the same integral over and over and over and over again. And so the cumulative distribution function would be the antiderivative function of that, right? But it'd be the definite integral from negative infinity up to some value x. See, I did it again. Let's use an x here. Sometimes we use a t up there. I think the book might use a t, because we oftentimes think about the random variable t in terms of time, but it doesn't have to be. And so this would be integrating my function, here I'll use a t here, from negative infinity up to some value x of f of t, okay? Which I know there's no probability up to 0, and then I start accumulating probability after 0. So when I go ahead and figure this thing out, it's going to be 0 if x is less than or equal, or sorry, less than 0. And then once I get to 0, then I'm starting to accumulate some probability. And so then whatever the antiderivative of this function is, or whatever I get out of this integral, will be the value I get there. And so I can write this as the integral from, if x is greater than or equal to 0, I could say 0 to x of lambda e to the negative lambda at t. Because really that's where my probability starts, is it starts at 0. Okay. And then again, the interpretation is moving forward in time. What's the probability I'll have to wait a certain amount of time until I have my first success. So I need to what? I need to integrate. I need to be able to find the antiderivative of e to the negative lambda t. And I go back and I think, oh yeah, if I need to e to the negative lambda t dt, what's the rule for finding the antiderivative? This is just a u substitution. But there's a nice, fairly simple formula. E to the negative lambda t over negative lambda plus a constant. Right. How do I know? Well, when I take the derivative of this using the chain rule, then the negative lambda from here and here will cancel out. It's a u substitution. If I let u equal to negative lambda t, and then do my substitution, I get the same thing. Okay. So if that's the case, let's see, then the antiderivative of this function would be lambda e to the negative lambda t over negative lambda, right? The same thing as that one there, and then I'll plug in 0 and I'll plug in x. And I see my negative lambda can cancel out with that and give me just a negative out in front. And then when I go ahead and plug in x, I'll get negative e to the negative lambda x minus negative, and when I plug in 0, 1. And minus a negative will be plus 1, and so it looks like it'll be 1 minus e to the negative lambda x. Okay. So what's that telling me? My cumulative distribution function says, okay, I'm computing all the area to the left of a certain point, right? And over here, there is no area. Right? And then I get past x equal to 0, and now I'm starting to accumulate area. At 0, it would take the value 1 minus 1 is 0. But then it looks like 1 minus some exponential function. It will, here's my height 1. Okay. As x goes off to infinity, e to the negative lambda x will be getting closer to 0, so I get 1 minus something getting close to 0. So I do have a horizontal asymptote there, and it will look something like this. Oops, I shouldn't have crossed it. Right? This exponential random variable. Right? So that's what the cumulative distribution function would look like in this particular case. Or actually with all exponential random variables. The only thing that changes is the lambda. The only thing that changes is how steep this is. Right? If lambda is a very large number, this thing's very steep and it goes. And if lambda is a fairly small number, close to 0, then it might be a little more shallow, and that's going to have the same effect over here. Does it go up like this and over, or is it a little more shallow and coming over? Okay. But all exponential distributions will look the same, except for that. Okay. So if we wanted to now, I'll just tell you the expected value of that will be 1 over lambda. Okay. But if we wanted to, we could calculate the median. That's what we'd call the mean. Okay. And because I have my cumulative distribution function, it would just be asking the question, okay, what value can I plug into my cumulative distribution function and get a 0.5, right? Get a 1/2, right? Which is really just saying, okay, 1 minus e to the negative lambda times q 0.5, 0 is equal to 0.5, right? And I'm just solving for this value right there. And how can I do that? Let's see. Well, I could subtract both 1 from both sides, and I could multiply both sides by -1, and I would say e to the negative lambda q 0.5, 0 is equal to, it's still 0.5. I could take the log of both sides, right? And then this would come out in front, and so then I'd have my, what I'd have, negative lambda q of 0.5 is equal to the natural log of 0.5. And then it looks like I could take this and I could take my natural log of 0.5. Oh, I could move this negative sign over here. And then the negative sign out in front of the natural log is the same thing as taking and raising that to the the negative 1 power. And 0.5 to the negative 1 is the same thing as 2. So that'd be like a natural log of 2. And then I'll just divide both sides by lambda. And I see my q to the 0.5, 0 is equal to 2, let's see, the natural log of 2 over lambda. So I want to point out, right, the median and the mean they do not have to be the same thing. Right, what I did here is I just figured out, okay, what value can I plug into my function here so that my cumulative distribution function takes the value of 1/2, and the answer is natural log of 2 over lambda. This one says, okay, if I take a large enough sample, and I take the sample from this distribution, and I add everything together and I divide by the number of samples I took, what value is it going to be close to? 1 over lambda. And those aren't the same thing. Natural log of 2 is close to what? 0.69 or something like that. So the median, sort of the middle value where half the probability to the left of that point would be over here. And the mean, right, the idea of being able to take a lot of values, add them up, and divide would be over here to the right of that. Okay. So here's an example of a median and the mean not being the same thing. So what we'll do next time, we can actually show this expected value calculation We could compute other interquartile ranges. We'll find some other things to say about this, but we can certainly, we'll look at some applications of these things. Oh, and I do want to show how is the exponential distribution, which is a continuous random variable, how is it actually doing something similar to the Poisson random variable. Again, this lambda here is the same for Poisson and the exponential distribution. All right, we better stop there because I want to get to the next stuff.